Hello everyone and welcome back to my session. Today we are going to talk about image processing and particularly images related to skin diseases or skin cancers. And within that, our focus is melanoma cancer detection. I have ISIC data for like different skin cancer diseases, and within that, I have around 4,500 images to start with. What I've done is I've built a neural network and trained the model, and with that training, I've got an accuracy or training accuracy of around 71 percentage and validation accuracy of around 62 percentage. But before even achieving this, I want to talk about three things that I have done. One, that I build a custom neural network model where it did not have any transfer learning and it performed quite badly, like around 30% of on an average accuracy was achieved. After that, I what I did is I moved into transfer learning. I used ImageNet as the transfer learning model and then trained that model. That achieved a significant good accuracy of around 65-70 percentage that I could see on an average. And then I moved, even with that, the validation accuracy was around 50 percentage. So I used technique called uh, augmenter, which like handles the class imbalance. So here, nine classes were there to be predicted. I'll tell you which are those nine classes or nine different skin cancer diseases. These are the ones. So, what is interesting is out of these nine skin cancer diseases, of which we have good number of images, around 2,357 images were there. Melanoma is one of the cancer which is like which causes or is uh, uh, having 80 percentage of death uh, due to melanoma skin cancer across all the skin cancer diseases. So it is very much important for any physician to detect as early as possible, and if you are able to detect early, then around 65 percentage of it is curable. So quite a good number if you detect early. So it is very good to have such kind of a app where you just click the photo, and after clicking the photo you can predict whether it is a melanoma or some other skin cancer disease. So this is how my model, where I learned, or where the model learned, and then I built an app for a quick demo. So three things that are noted here is one, like a custom model, how did it perform? After that, adding transfer layer model, how did that perform? And even after transfer learning, it was not doing good because there was class imbalance. When I say class imbalance, one particular one particular skin cancer had more images versus other. So what happens while training is it has bias for a particular skin cancer versus another, like it overlearns a particular image class, and that is the reason the output, more often than not, it will come out to be someone where it learned a lot. Like, let's say if a particular skin cancer was pigmented benign keratosis, and it has a more number of images, like out of 100, 30 or 40 images are of one class, then it overlearns this particular skin cancer. So whenever you upload an image and see, it will have this output. So that was seen here, and that is the reason of what I did is I used an augmenter which kind of rotates a particular image and creates a copy out of that. Not just rotation, it performs different types of small changes to the same image, and still retains 90 to 95 percentage of data. So it has it has different types of images to learn for the same class, and handles the imbalance by having all the nine classes same number of images. So that that way, when you then if you feed this to the new to your neural network model, it gives you a better output. So this is all for today's session. Do let me know your thoughts on how like we can improve better, because even with transfer learning and using augmented technique for handling class imbalance, my validation accuracy is suffering a lot, like it is just 61 percentage. So overall, all these are convolutional neural networks. They are good at feature extraction of images, and the ImageNet in itself is like trained um, model. Even after all these things, like the validation accuracy is not that great. So we would want to have go to an accuracy of 90%. My I feel that the number of images for training this model, that itself were far too low. So that could be one of the reasons that it is not able to train well. If we get more data, more quality inputs, the model should be able to learn better, because overall the architecture seems good. If we talk about architecture, I'll just quickly show you how the architecture looks like, the last architecture. This is my architecture, where the first layer is the mobile net layer, and that's the base model. After that, there's a global average pooling that we are doing here, and there are dropout, which kind of tries to regularize and avoids overfitting. Then there is a dense layer with a ReLU activation, and then another dropout layer to avoid overfitting and regularization. And then finally we have number of classes dense layer. The number of classes is 9 here, so there will be 9 neurons, and the activation is softmax. That means that all the classes will have their own probability, and the probability of for a class which is the highest will finally be selected. That's my latest one. And before that, my first model, which was a custom model without any transfer learning, that model I'll just show you. This is it. So where we used first layer as a rescaling. So all the pixels were scaled and like divided by 255. So it's a normalization that we are doing. Then there is a convolutional 2D layer with 16 as like the 16 is the filter size. So it will kind of learn 16 features. I could be wrong, but that's the overall idea. Then there's a max pooling 2D. That means it tells you the like the most important feature that is learned. So kind of averages and gives you still retains the most important part of the convolutional layer, reduces the number of the size of it, so that it is good for like overall further processing. Again, the layer continues convolutional 2D 16, then max pool 2D. The second layer, it learns further patterns. Third layer is also the same thing. Ideally, what I've observed is this could have been from 16 to 32 to 64, so that it generalizes and understands more complicated patterns better. But for my processing part of it and for experimentation purpose, I had three layers here with 16 as a convolutional size, and ReLU activation was used here to to get learn nonlinear relations as well, and dropout for regularization. As we know, flatten is to flatten and get a 1D dimensional data, because the next layer dense, it expects a 1D dimensional input. So here, and then there is a dense 8. It's an 8 neuron fully connected layer with a ReLU activation. Then there's a dropout for regularization, and then finally 9 dense layer neuron fully interconnected with each other with a softmax that gives you the probability of each class. So that was my initial first model that I had did, and total parameters were around 56,000. So too much of information maybe for someone who has not worked upon neural networks and image recognition. And epochs were 10 year. accuracy, as I mentioned, was 28%, and validation was just 17%. So we were, with the transfer learning, we almost tripled the accuracy that we had gotten with just um, a custom model, that model architecture that we had used. So as I mentioned, the model is still not performing that good with 65 to 70% of validation accuracy. I don't think it's a good model to start with. But maybe with further optimizations and adding good quality data, should be able to achieve more than 90-95 percentage of accuracy, and that will really help physicians detect melanoma cancer at a very early stage. And this app, by just uploading the image of their skin, should be able to predict whether it is a melanoma cancer or some other type of a skin cancer. So that's all for today, and do let me know your thoughts and feedback on this session. And thank you so much.